All right, you know that feeling, right? You're cruising down the highway, maybe on a road trip, maybe just heading home, and bam, that little light pops on. Time for gas. And it's like, what, 5 minutes later, maybe less? They're back on the road, tank full, easy. It's just baked into the American driving experience, generation after generation. Honestly, I remember seeing an EV owner just like patiently waiting at a charger, scrolling their phone. It felt like forever while I was in and out of the gas station in minutes. It really hammered home that difference in rhythm, didn't it? But like me, you've definitely started noticing more of them, right? Those electric cars, that quiet hum as they glide by, almost silent. There's a real buzz around this electric future, cleaner air, quieter commutes, yeah. A whole new way of thinking about travel. And it's happening. I mean, nearly 1 in 5 new cars sold in 2023 were electric or plug-in hybrids. That's a big shift. But for all the excitement, there's this one major hurdle that keeps popping up. It's not always range anymore, or even the price. It's that 5-minute gas stop versus the current reality of EV charging.
We're talking hours overnight at home, maybe. Or even with the fastest public chargers, you're looking at, 15, 20 minutes just to get enough juice for the next leg.
It absolutely is the big sticking point. And that charging time difference, it creates some very real practical problems. It goes way beyond just convenience for, the average driver. Think about someone living in an apartment in a big city, no dedicated spot to charge overnight. Where do they plug in easily?
Yeah, that's a tough one.
And for businesses, delivery companies, for instance, their fleets need quick turnarounds, hours of charging. That's lost productivity. That hits the bottom line hard. It's not just a minor hassle. It really changes the economics of running an EV fleet. And what's really fascinating is how the goalposts have moved for fast charging.
Oh, yeah. How so?
Well, maybe 10 years ago, getting a decent charge in 15 minutes, that was considered, cutting edge, fast. But now, car buyers are demanding that 5-minute experience. They want it to feel like filling up with gas.
That 5-minute refuel.
Exactly. And it's not just what consumers want, it's becoming a critical barrier for mass adoption. Plus, it's a big deal for the charging station companies, too. Faster charging means more energy sold, more customers served per day, often at higher prices.
Right. More throughput.
It's a win-win, really, if they can crack the code.
So that's the mission today, isn't it? How do we bridge that gap from hours or even 15, 20 minutes down to that magic 5-minute charge? We're going deep into the science, the engineering, looking at the revolutionary changes happening in batteries. Get ready, because we're going to uncover some pretty surprising stuff about how that 5-minute EV charge might actually become reality.
Yeah.
Okay, so let's dive in. To get to 5 minutes, we need to understand what's actually slowing things down inside the battery.
Yeah.
Where are the log jams? What are researchers really scrutinizing?
Right. So let's do a quick battery 101. You've got 2 electrodes. The positive one, the cathode, and the negative one, the anode. And in between, there's this conductive liquid, the electrolyte. When you're driving, electrons flow through the car's circuit, powering everything. At the same time, inside the battery, tiny charged particles, lithium ions, move from the anode to the cathode through that electrolyte.
Okay, got it.
Recharging, it just reverses that whole process. The lithium ions have to travel back into the anode. Now, when you try to do that really fast charging, the main bottleneck almost always is the anode.
The anode, okay.
Yeah. While we've seen lots of progress in cathode materials, things like NMC, that's lithium nickel manganese cobalt oxide, or LFP, lithium iron phosphate, popularly for different reasons, energy density or cost. The real focus, the intense work for speeding up charging right now, it's happening at the anode.
So what's the deal with the anode? What's it usually made of?
Historically, it's graphite. And graphite's great in many ways. It's cheap, it's everywhere, non-toxic, conducts electricity pretty well. And critically, it has this layered structure. Think of it like sheets of paper stacked up.
Okay.
Lithium ions can kind of slip in between those layers.
Sounds ideal. So what's the problem?
Well, that layered structure, that 2D nature, is also its limitation for speed. When you're trying to jam ions back in super quickly, imagine like 1,000 people trying to leave a big meeting hall, but there's only one small set of doors.
Right.
Yeah.
A bottleneck.
Exactly. Even if everyone wants out fast, the doors limit the flow. Same thing with ions trying to get back into graphite quickly during fast charging. They kind of queue up.
That's a great analogy. So if graphite is this meeting hall with too few exits, what are engineers doing? Just tweaking it? Or are they building whole new wings on the hall? What are the radical ideas?
Oh, they're definitely trying to build new wings, maybe even new doors. Some really radical stuff. One fascinating approach, actually from a U.S. patent by researchers at the Department of Energy's National Renewable Energy Lab. They've literally been drilling tiny holes in the graphite using lasers.
Drilling holes.
It's just
Tiny ones, like 5 micrometers wide, really small. But these little channels create way more surface area, more entry points for the ions to get into and out of the graphite structure. And their reports show batteries with these laser-drilled anodes can charge more than 3 times faster.
Wow. So just opening up more doors.
Pretty much.
Wow.
It's a clever way to boost speed without totally ditching graphite.
Huh.
But then there are candidates to replace graphite altogether. Silicon is a big one. Silicon, like in computer chips.
Kind of, yeah. It's also abundant, inexpensive, generally safe. And here's the kicker. Theoretically, silicon can hold way more energy than graphite. Think like 1 lithium ion for every 4 silicon atoms versus 1 for every 6 carbon atoms in graphite.
So more energy in the same space. Smaller batteries for the same range.
Potentially, yes. That's the big draw. More energy density.
Okay, sounds amazing. So what's the catch?
There's always a catch.
You got it. And it's a big one for pure silicon anodes. When silicon sucks up those lithium ions during charging, it swells massively.
A swelling.
Over 300% in volume.
Whoa. Compared to graphite.
Graphite only expands maybe 10%, so 300% is huge.
Yeah.
And that massive swelling causes the silicon anode to literally crack and pulverize over time.
Ouch. So the battery just falls apart.
Essentially, yeah. This cracking drastically cuts down the battery's lifespan, maybe by years. Especially with repeated fast charging cycles. We're still figuring out exactly how long these pure silicon batteries would last in the real world in an actual EV, but it's a major, major concern. Right. And that brings up a big question for you, the listener, doesn't it? Is getting that super fast charge worth having to replace your battery pack or maybe even your whole car way sooner? I mean, nobody wants a phone that charges in 30 seconds but dies after a year. It's a huge trade-off engineers are grappling with.
Absolutely critical balance, which is why a lot of focus is now on hybrid approaches, like silicon-doped graphite.
Okay, so mixing them, how does that work?
Imagine weaving tiny, super-fast silicon highways into the sturdy, familiar graphite structure. There's a company, 1D Battery Sciences, doing something really cool. They actually grow tiny silicon nanowires inside the pores of graphite particles.
Nanowires inside the graphite.
Yeah, it's pretty clever. You get the best of both worlds. The lithium ions can zip into and out of those silicon nanowires about 4.5 times faster than graphite alone. Huge speed boost.
Okay, addresses the speed.
Right. But the surrounding graphite provides the structural support. It helps manage that silicon swelling, conducts current, and, really importantly, it helps pull heat away. Heat is another killer for batteries.
So the graphite acts like a scaffold in a heatsink.
Exactly. It's like getting the speed of silicon without the catastrophic cracking problem. This approach really tackles the biggest practical hurdle for using silicon.
That sounds very promising. Is it close to being in cars?
Well, 1D opened a pilot plant in Washington State this year, 2024. They're planning a bigger one. But integrating totally new battery tech into mass-produced cars takes time. Lots of testing, scaling up manufacturing. So realistically, you probably won't see these specific silicon-doped graphite batteries in EVs much before 2030.
2030. Okay, so still a ways off, but progress.
Definitely progress.
Yeah.
Exciting progress, but yeah, patience is needed.
So you're right. There's clearly no single silver bullet here. It's a multi-pronged attack on this 5-minute goal. We've talked anodes, drilling graphite, adding silicon. What else? What other angles are researchers exploring?
Oh, lots of different angles. It's not just about the anode material. For instance, there's another anode material candidate, lithium vanadium oxide. A company called TieFast is working on this. Now, their batteries currently have lower energy density, meaning for the same range, the battery pack would have to be heavier and bigger than what we see in most cars today.
Heavier. Less ideal for passenger cars, maybe.
Probably. But here's the trade-off. TieFast claims they can get a full charge in just 10 minutes.
10 minutes. That's close. Why so fast?
They say it's because the lithium ions can just hop really rapidly through the crystal structure of this material. Very efficient movement. So while maybe too bulky for your average sedan, that lower energy density isn't such a big deal for, say, heavy commercial vehicles. Think mining trucks. They're already huge.
Right. Weight isn't the primary concern there. Speed is.
Exactly. And this research, interestingly, is funded by a U.S. Department of Energy program called ARPAE EVS4AWOL, their specific goal, an 80% charge in just 5 minutes.
So the government is pushing for this too.
Definitely. Another EVS4 AL project involves Ohio State, Honda, and Argonne National Lab. They're looking at anodes made from glassy materials. Their focus is a bit different. Smaller, maybe more affordable battery packs, perhaps with shorter range, but with that extremely fast charging. Think quick urban delivery routes.
Tailored solutions, then.
Precisely. Though a challenge there is making US-made batteries cost competitive with imports. That's a whole other puzzle.
Okay, what about improving what we already have? Any gains there?
Absolutely. Look at the Chinese battery giant, CATL. They're making huge strides by optimizing existing chemistries. They work with LFP, lithium iron phosphate, which is a common, cost-effective cathode material, but they process it differently. Instead of using typical binders, they press the powdered LFP directly onto a conductive foil.
What does that do?
It makes the electrode thinner and drastically reduces electrical resistance. Less resistance means ions move faster charging. Their Shenzhen Plus's battery claims it can add 600 kilometers, that's over 370 miles of range, in just 10 minutes using their own fast chargers.
10 minutes. For that kind of range, that's impressive using existing materials.
It shows how much clever processing and engineering can achieve. And we can't forget the electrolyte that liquid the ions swim through.
Right, the medium.
That can be a bottleneck too. So researchers are playing with the recipe. Using lighter co-solvents, like methyl acetate, can actually double the electrolyte's conductivity. It basically prevents those ion traffic jams near the anode during fast charging. Smoother flow, faster charge.
So it's the anode, the cathode processing, the electrolyte, it's the whole system.
The whole system, exactly.
Okay, so beyond the physical materials inside the battery, what about controlling it? Software, charging systems. Are there smarter ways to manage the charge?
Oh, absolutely. Software is playing a massive role already. Take Tesla. Their battery management system, the BMS, is pretty smart. When you use the navigation system and set a destination for one of their fast chargers, the car's software actually starts preheating the battery on the way there.
Preheating, why?
Because batteries charge faster when they're warm. The chemical reactions speed up, the ions move more easily. It's a subtle thing, but it shaves off real time at the charger without changing the battery chemistry at all. Just smart software.
Clever. What else on the system level?
Higher voltage charging is another frontier. You see companies like BYD pushing this. They recently announced a new 1500-volt charging system. For context, Tesla's superchargers run around 1,000 volts.
1,500 volts. That's a big jump. How does that help?
More voltage means you can push more power faster. BYD claims their system can add 400 kilometers, about 250 miles of range in just 5 minutes.
5 minutes. There it is. How do they handle that voltage?
They use advanced semiconductor chips, specifically silicon carbide, or SiC, in the car's onboard charger. SiC chips are tougher than regular silicon. They can handle higher temperatures and higher voltages much more efficiently. That's key to moving that much power that quickly without things overheating.
Wow. Okay, 1,500 volts, 5 minutes. But again, my first thought is, what does that do to the battery long term? Does that kind of speed a free lunch?
That's the million-dollar question, isn't it? And no, it's definitely not a free lunch. Pushing that much power that fast, it gets tricky. Very high voltage charging can seriously accelerate battery degradation.
Wow.
Remember how ions need to slot neatly back into the anode? When you flood them with electrons at super high voltage, sometimes they don't make it. Instead, they can turn into lithium metal plating onto the anode surface.
Plating, like chrome plating.
Sort of, but unwanted. This lithium plating is usually irreversible, and it eats away at the battery's capacity over time. Worse, these deposits can form sharp, spiky structures called dendrites, like tiny needles.
Needles inside the battery. That sounds bad.
Very bad. If those dendrites grow long enough, they can pierce the separator between the anode and cathode. That causes a short circuit, potentially, thermal runaway, fire. It's a major safety concern.
Yikes. So how does BYD manage that?
Their software almost certainly has sophisticated algorithms to monitor temperatures, voltages, and current very carefully to try and minimize this plating and dendrite growth. But it highlights a huge challenge. It's not just about building a 1500V charger. You need the cars to handle it safely and the batteries to withstand it long term. Plus, widespread adoption of 1500V charging would mean building out entirely new charging infrastructure. That's a massive undertaking.
So it's complex. It's not just one thing.
Not at all. An Argonne researcher, Venkat Srinivasan, actually predicts the solutions will roll out in phases. Phase 1, software tweaks, like Tesla's preheating. We're seeing that now. Phase 2, better architecture and processing, like CATL's pressed LFP. Also happening now. And phase 3, the longer-term play, will be those entirely new materials and chemistries, like advanced silicon or other novel anodes. Those aren't quite ready for prime time across the board yet.
It really is remarkable, isn't it? The sheer ingenuity involved here. When we started this deep dive, I think I half expected one single breakthrough, the magic bullet, but realizing it's this intricate dance. Materials, science, chemical engineering, clever software, system design, all working together. That's really fascinating. Getting to that 5-minute charge is clearly one heck of a complex puzzle.
That's a perfect way to describe it, a complex puzzle with lots of pieces. And it really underscores that idea of trade-offs in battery design. There isn't going to be one single perfect battery for every single EV. As one researcher, Chong Yan, pointed out, different applications need different solutions. You might have a bulkier, maybe slightly lower energy density battery that charges ultra-fast for a mining truck, while a passenger car might prioritize energy density and longevity, accepting a slightly longer charge time, maybe 10 or 15 minutes instead of 5. We're going to see tailored solutions emerge. Understanding those compromises is key.
So as you go about your day, maybe driving past a charging station, think about this. If EVs could truly recharge in 5 minutes, just like pulling up to the pump today, how might that change everything? Our reliance on personal cars, the shape of our cities, even long-haul trucking across the country. What stands out to Wei Yu is the most surprising piece of this puzzle, the most impactful insight from our deep dive into the race for the 5-minute charge.